So we're going to be exploring maximum and minimum values and what makes a point a critical point. So as you can see, this curve we have here, we are decreasing, then increasing to a cusp, and decreasing again. So first of all, we have to think about what makes a critical point a critical point. Since this is decreasing along here, we know that on this section, f prime of x is less than 0. And increasing on this side means f prime of x is greater than 0. And same with decreasing on this side, f prime of x is less than 0. So in order for a critical point to be a critical point, we have a point C and f of C, which is defined as a critical point, as C as being a critical number. So here, we know that at this tip, we have a horizontal tangent line. That means that when the derivative is equal to 0, at the point x is equal to -1. Therefore, x is equal to -1 is a critical point. We also have a critical point when the derivative is undefined. The derivative is undefined at a cusp. So there's two times we have a critical point. We have a critical point when the derivative of the function is equal to 0, and we also have a critical point when it's undefined. So in this example here, we would have a critical point at -1, and we would also have a critical point at x is equal to 5. So here's we have our two critical points listed. So moving on to 4.2, the sections is critical points with local maxima and local minima. So we can find whether there's a local maximum or a local minimum by using the first derivative test. So we're going to let f prime of c be equal to 0. If f prime of x changes from negative to positive at a point x is equal to c, that means the function has a minimum at that point. So basically what that is saying is if a function is going from decreasing to increasing, the point at where the direction changes is c, and that becomes a minimum, as you can see there. On the other hand, if f prime of x changes from a maximum, if f prime of x changes from positive to negative at a point x is equal to c, f of x has a maximum at that point. So when the derivative changes from positive to negative, that means at a point c, we are increasing, positive, going to negative, decreasing at this point c. And as you can see, as we go from increasing to decreasing, we have a maximum at the point c. So as we saw in the previous example, f prime of c when equal to 0 may imply something else other than a maximum or minimum. It also shows where the derivative does not exist or undefined. So that basically means at a cusp or corner like we saw in the previous example. But even though it's undefined at that point, it is still a critical point. So just like in this example where the slope is equal to 0, so f prime of x is equal to 0, and also where the function is undefined, those became our two critical points. So far we have an algorithm in curve sketching. We know that we can use f prime of x to find critical points. We can use our first derivative test, so using the intervals like you did in finding increasing or decreasing functions. So by using that first derivative test, we can determine whether f is increasing or decreasing on either side of the critical points that we find. Step 3 would be, upon step 2, we can conclude whether there's a local maximum or local minimum or neither. So basically, if we conduct our first derivative test and we see and analyze the intervals, if the interval is going from a negative interval to a positive interval, that means that critical point is a minimum. If the interval is going from a positive interval, meaning increasing, to a negative interval, meaning decreasing, that means that critical point would be a maximum. Tangent is parallel to the horizontal axis when f prime of x is equal to 0. So that just means a horizontal tangent line. So as you know, here's the horizontal axis. So all this is saying is a fact. So a tangent line, that is, if we call this a tangent line, if it's parallel to the horizontal axis, that means that the slope of this tangent line is also 0. So let's take a look at some examples. So we're basically going to use our knowledge of increasing and decreasing functions and also critical points to determine whether there's a maximum or minimum at those critical points. So if we're given this function, negative 6x cubed plus 18x plus 18x squared plus 3. And we want to find where the critical points are, that's what CP means, and if there's maximum or minimums. Our first step is going to find our critical points. So we're going to set our derivative equal to 0. So the first step is to find the derivative, factor it, and then set it equal to 0. So when we set both these factors equal to 0, we find our critical points to be 0 and 2. And there we have it, x and 0, x is equals to 0, and x is equal to 2 are our critical points. Step 2 would be to use the first derivative test. So here we have our f prime of x there should be an x there, sorry. So we have negative 18x, x minus 2, as our f prime, and we also have our intervals. So we have our critical numbers 0 and 2, and we're going to set it up in our number line or in our chart using intervals. So if our critical points are 0 and 2, we have the interval x is less than 0, x is in between the critical points, and x is greater than 2, our greatest critical point. If we put in any number less than 0 here, let's say we put in a -1, for example. If we put in a -1 for the value for f prime of x, we would then result in a negative number. Negative 18 times -1 is positive 18. Positive 18 times -1 minus 2 would give us a negative number. Then we're going to put in a number between 0 and 2 and see what we get in that interval. So let's plug in 1, for example, a number in between 0 and 2. If we plug in 1 into this interval, we would get a positive interval. If we plug in a 1 into our derivative, we would have negative 18 times 1, which is negative 18, 1 minus 2, which is negative 1. A negative times a negative is a positive. And lastly, for our interval greater than 2, we can plug in any positive number greater than 2. If we do so and plug it into our derivative, so any number, let's say we plugged in 3 here, we would always get a negative number. So these intervals represent what is actually happening in our function. When x is less than 0, we are decreasing. However, on the interval between 0 and 2, So we are decreasing when x is less than 0. On the interval of 0 and 2, we're increasing, and when x is greater than 2, we're decreasing. What this means is we're going from a decreasing interval to an increasing interval at the critical point 0, which means x is equal to 0 must be a minimum. However, here, the function on this interval is going from increasing to decreasing, which means at the critical point 2, we must have a maximum. So now our last step is just to state what we have. So like I said, we have a local minimum at x is equal to 0 and a local maximum at x is equal to 2. Now, how we find our actual points is we must plug in 0 and 2 back into our original f of x, because now we're just trying to find the coordinate point. We have the x coordinates, and we must plug them back into f of x to find the y coordinates. So we plug in 0 into f of x and get 3, and we plug 2 into f of x and get 27. Reminder, we're plugging the critical point into f of x, not into the derivative of f of x. And from there, we get our local minimum to be at 0, 3, and our local maximum to be at 2 and 27. So we could take a look at a different example. So this example actually it involves lawn. So we can take a look at this one, but it still gives you the same process. Let's look at an exponential. When looking at an exponential function, we can still determine the local extrema the same way. So what we would do initially is step 1, just like in the other question, set the derivative equal to 0. So first of all, we have to find our derivative, factor, and set our derivative equal to 0. When we do so, our x squared eliminates in the denominator because we're multiplying both sides by x squared. So now we get 0 is equal to 2 to the exponent x, and 0 is equal to the other factor x ln 2 minus 1. We actually cannot solve for x here because there's no value for x that 2 to the exponent x would give us 0. However, we can solve for x in this question. We just rearrange and solve for x is equal to 1 over ln 2. So in this question, we can look from our f of x that already from here, x cannot be equal to 0, or else we would have 0 in the denominator. So what that means is there's actually a vertical asymptote there. We'll explore this topic a little further in other sections, but we know that we can't have 0 in the denominator, which means we have a vertical asymptote. So we're going to do our first derivative chart as step 2. So we have our intervals from 0 to our critical point that we found, x is equal to 1 over ln 2, all the way to infinity. So the reason why we start at 0 is because we have an asymptote, and we don't go all the way to negative infinity because we cannot have a negative number in our derivative. So you have to think of your domain as well. So we have our domain in our intervals and our critical point. Now we can see where there's a local maximum or a local minimum. So we have our interval. We input our derivative. So our derivative being what we found above here. So we're using this derivative and plugging in numbers. So we're plugging in a number between 0 and 1 over ln 2. 1 over ln 2 is about 1.443. So let's plug in, for example, 1. When we plug in 1, we end up getting negative 0.614. Let's take a look at a number bigger than 1 over ln 2. Let's say 2. When we plug 2 back into our derivative, we end up getting 0.3286. So if we investigate our signs, when x is in between 0, 1 over ln 2, our value is negative, meaning it's decreasing. When we're greater than 1 over ln 2, it's positive, meaning we're increasing. So from what we've learned, when we go from a decreasing value to an increasing value, that means our critical point has a local minimum. So we just have to find where our local minimum is defined by plugging in our critical point, 1 over ln 2, back into our f of x, where we get e ln 2. So now we have our critical point, e ln 2, is equal to approximately 1.884, so this becomes our local minimum. We can use that to actually graph our function. So by doing so, we have 1.443, and 1.884 to be our local minimum. And we also have a vertical asymptote at x is equal to 0. So that's how we would explore how to graph maximum and minimum of functions by using critical points, local increasing and decreasing, to find our local maximum and minimums.